Hello, everybody. Today, Alexei Kotov, one of the organizers from Hradec-Kralove, should be here in our lecture room to present his lesson on the Z-graded manifold, and in a sense, a continuation of the Vladimir Salnikov, right? Last year, talk also on.
Formally, even it was 2022, but at the very end of 2022. So, and you are completely right. Thank you very much for letting me talk here. It's always a pleasure to be in Prague, and especially at this institute. So, as one said, she is totally right. So this is a continuation of the talk given by Volodya Salnikov about 1 year ago here, and this was about the category of Z-graded manifolds. And there will be some other talk on 6th of March, which I highly recommend to listen. There will be Sasha Goncharuk talking about Kashut-Tate resolutions and some particular way of constructing them. It should be very interesting. I suggest, really recommend to listen to him. So here I wrote the 3 references, and actually what I will talk about is more about the first one. It's a joint paper with Vladimir Salnikov and Camille Laurent-Gengoux from Metz, and this is about Z-graded. They don't see it? Okay, is it fine? Okay, so if you see what's written here, so there's I will tell you. So the first paper is called Normal Forms of Z-graded Q-manifolds, and this is a joint work by Camille Laurent-Gengoux, Vladimir Salnikov, and me, published in Geometry and Physics, Journal of Geometry and Physics 199, 2023. And this is a sequel of another paper, number 2, the category of Z-graded manifolds, joined with Vladimir Salnikov, which is going to be published in Differential Geometry and Applications this year. And I recommend another reference, which is also a sequel of number 2, which shows some examples how to use Z-graded manifolds. And this is called Various Instances of Hradec-Kralove pairs, again by me and Vladimir Salnikov, published in Geometry, Journal of Geometry and Physics 191, 2023. If you see the same journals, it's not a mistake. It's really the same journal. And actually, the third paper was a kind of motivation for us to look at the graded manifolds. So before, a few years ago, we published another one with Benoit Joubin and Norbert Pansan, where we constructed Lie theory for differential graded Lie algebras, which was maybe first written completely in a complete formal way. Also, the idea was a kind of folkloric, but still. And then we did this for, we started doing this for Z-graded manifolds, but finally we did it for N-graded manifolds and figure out that we do not have enough formalism to construct in the pure Z-graded case. And then we started looking at number 2, and then we finalized at number 3 the original idea about Hradec-Kralove pairs. Like 3 was a very natural, was a motivating example, and in the same way, a very natural application of number 2. And number 1 is basically what I will talk today about. Okay, first of all, I assume that people here are familiar to a certain extent with supermanifolds. So I don't need to repeat all this stuff, right? So and maybe some people know it very well, but so it's not to talk about supermanifolds. First of all, what do we know about Z-graded manifolds? And first about Z-graded vector spaces and Z-graded algebras. So a Z-graded vector space at a direct sum here we've used as a direct sum of vector spaces concentrated in degree I, and I goes from minus infinity to plus infinity, takes values in Z. We do not assume that this vector space has only finite number of non-zero components, but we in this talk we'll always assume that the dimension of each VI is finite. Then like in the super case, we can also construct the notion of Z-graded algebras, in particular Z-graded commutative algebras, but for commutativity we'll need some extra data. So a Z-graded algebra is an algebra which is decomposes into the direct sum of AI. We cannot assume now that the dimension of AI is necessarily finite. It will be actually many situations it will be infinite. But what we require is that the product of AI and AJ belongs to AI plus J. Or we can also say that there is a derivation epsilon, which is called the Euler derivation. Euler derivation, such that epsilon restricted to AI gives I times the identity. Okay, so now I will tell commutativity in a second. So to tell us something about commutativity, we need to have some gradient, right? We need to have some sign rule in this case. And in the super case, we know that the sign rule is given by Z2 gradient, right? And we know that for two elements A and B, which belongs to A, so the supercommutativity means that if A belongs to AI and B belongs to AJ, AB equals to -1 to the power IJ BA. Here, in the case of Z-graded algebras, we do not have an a priori Z2 gradient. So there is a natural choice which is very popular. So this the first choice is Z2 is Z modular 2, right? And then of course, whenever we have such a choice, we can produce some super gradient. But in general, it's not necessarily true. For instance, it's not necessarily the case. So in principle, what we require that the Z2 gradient and Z gradient are compatible. Sorry. It means that each AI is a super vector space, or each component of parity of odd and even parity is Z graded. So if you produce, manage this by using two Euler vector fields, one is Z gradient and the second is Z2, it will mean that they are commuting. So in principle, it's always possible that everything is commutative in a general case. It's still if we take just polynomials, they will give us an example of Z-graded algebra, which will be just commutative. It's also possible. Now, if you want to produce out of this, if you want to produce some manifold, then we should have to produce a manifold. There are natural ways to have some ringed space. So it's a sheaf of algebras. It means that over each, so our manifold is covered by some coordinate charts, and over each coordinate chart we have some algebra. And over double overlap there is a change of coordinates. So the first question, of course, is what is the local model? What kind of algebra is living over open set? What is a trivialization of this? And of course, it's natural to consider an algebra generated by some coordinates. Actually, in this talk, we'll talk about what my course Camille Laurent-Gengoux usually calls Z-star graded case. I will tell what it means. So it means that locally we have some coordinates in degree 0, which are coordinates on the base manifolds. So there are no further coordinates in degree 0. And also some coordinates, let's say psi alpha k, such that the degree of psi alpha k equals to k, which is not 0. So it goes from -infinity to infinity, but it cannot be 0. Then the first naive choice is to look at polynomials if you're in the smooth category. So the first naive choice is just to do what we always do in supergeometry. Look at polynomials of non-zero degree variables whose coefficients are smooth functions of 0 degree variables. During this talk, I will talk only about smooth case, because analytical and algebraic cases is more complicated. I will tell why. So it's everything is smooth, everything what we expect will work. So the first choice is polynomials. But here we face some polynomials of psi alpha k and smooth functions of xi. And here, if you do this, now it really depends on what kind of coordinates we have. If there are coordinates of only positive or only negative degrees, in addition to 0 degree coordinates, then this will work perfectly well. But there is a possibility, so if degrees of psi alpha k are always less than 0, or degrees psi alpha k is always greater than 0, it perfectly works perfectly. But now let's consider the more general case. Suppose we have coordinates of mixed degrees. Now, as I said, to construct a manifold, we need to know how to glue two different local models over different charts. And let us look at the following gluing. Suppose here we have coordinates x, the simplest case, x, psi, let's say xi2 and xi minus 2. Here of degree 0, here of degree 2, here of degree minus 2. And here we have coordinates y, eta 2, and eta minus 2. Okay, so I put here even degrees to avoid any questions about the parity by the end of the day. Now, and let us take the following change of coordinates, which the natural requirement that the change of coordinates preserve the z degree. Otherwise, it's not z grade, it's something else. So let's take the following change of coordinates: y equals to x plus eta, not eta, psi 2, psi minus 2. This is even. And okay, eta 2 equals to psi 2, and eta minus 2 equals to psi minus 2. So it's easy to see. Well, you can easily believe that this is a good change of coordinates, which respects the z gradient, because it's of degree 0, it's of degree 0, right? It's the degree is preserved. Here, the degree is preserved. Right?
Sorry, but I know only example of a trivial class space. Can you show some?
Trivial what?
I mean, that's the only algebra of vector space. So you say about the manifold, that means only the nonlinear example.
I want to glue two models. Yes.
Before going to very much detailed analytical, can you give some example? That's why you want to consider such of the manifold, nonlinear one.
Well, so of course there are plenty of examples, but okay, the first example is 0 degree manifold, right? As usual.
I said that interesting. That means that not nothing that people didn't know. Yeah? Interesting that people didn't know, but nevertheless is the motivation.
So let me tell you that in the smooth case, all examples are of the following form. So it's a vector. Which one?
That okay.
No. Let's try it right first. Maybe this one here. Okay. So in the smooth z graded case, it's always of the following form. So we have a vector bundle graded by integers without 0. So this is z without 0, leaving over some 0 degree usual manifold.
Yes.
And then we look at functions here. And then we explain what kind of functions we need to look at, right? But finally, in the smooth case, all Z-graded manifolds will be isomorphic to this example. It's the Batchelor theorem. The Batchelor theorem works well. In the analytical algebraic case, it's no more true. And actually, in this paper, it's paper number 2 with Vladimir, we have counterexamples as usual, where in the analytical algebraic case it doesn't work. But in this most situation, it's always like that. There's the question: what kind of functions do we need to consider? And here, how it's written here, of course, polynomials as well. Polynomials are good. We can look at polynomials, symmetric functions on E or E star. But if you want to glue it, to try to make a theory out of it, we need to have some good change of coordinates. And the good change of coordinates is everything which is invertible and homogeneous with respect to Z gradient. And then let's look at this example. So first of all, y is of degree 0, it's of degree 0. This is 2 minus 2 is of degree 0. Y2 xi2 degree 2 minus 2 minus 2 degree minus 2. So the degree is preserved. Also, it's easy to see that it's invertible, right? So this is a very good change of coordinates. Now, if you want to look at the smooth case, we have to be able to consider smooth functions of 0 degree coordinates. Otherwise, it's not smooth, right? And now the simple argument. Let's take the cosinus of y, right? So this will be the cosinus now of x plus psi2 psi minus 2. And so that now, just to make sense of all of it, we have to decompose here the Taylor expansion. And in contrast to the super situation where all series are polynomials, here we'll get a formal power series, which tells us that polynomials are not sufficient. And then we looked at how to make it regularly. So what kind of functional space we need to consider. And here we found the following simple idea. So let's construct the space as follows. So first of all, it's even more general. So suppose A is a Z-graded, and assume it's also supercommutative with respect to some Z2 gradient, which is here it's not that important. Algebra. So A splits into the direct sum of AI, where I goes from minus infinity to plus infinity, right? Now we can introduce the following filtration. So let's consider Fi of A, and this is the ideal generated by, here one needs to be important, one needs to be careful because it's not precisely how it's written here. It's the ideal generated by the sum of Aj for all j less or equal to minus I. Okay, this some rule by here is I minus I, so you can just believe that after some iterations we came to this notation. But in principle, it can be positive, it can be some other notation. But what is important that we take the sum of Aj for j less or equal to something, or maybe greater or equal to something. This will give a similar technique, but one needs to be careful which one is chosen. It's not, in general, it may be not even an algebra, but for sure it's not an ideal. How it's written, it's not an ideal, right? Because there is something of positive degree. If you multiply, we'll break this rule in general. However, if you generate an ideal like this, it will become an ideal by definition, right? So then you'll have the following filtration. So F2 of A belongs to F1 of A, which is inside F0 of A, which is of course A itself, and so on. So we'll obtain some decreasing filtration. And now what can we do? We can take the quotient A by Fia and take the the projective limit for I goes to infinity. And what we'll have will be the completion of A. So this completion a little bit different from the usual power. Even in the polynomial case, it will be different. In general, it's not the same as a power completion with respect to powers of the polynomials. But of course, how it's written here, it works for every Z-graded algebra. And now what is actually very interesting that it's remarkable. It's related to the Bachelor theorem that whenever we have such a construction, then A hat, the completion, will be again filtered again, right? Because the filtration will come from the filtration of A, as usual. Just this is a very general statement. It means that A itself will be filtered and Z-graded. If you take the adjoint, how it's called, adjoint factor, right, associated factor, Z-graded algebra with respect to the filtration, you'll obtain an algebra which will be Z2 graded. It will have two Z-graded gradients. And this is related to, this will give us a factor from Z-graded algebras to Z called Z2 graded algebras. And this related to the Bachelor theorem we'll talk about later. So now let us come to the Z-graded manifolds. Now the idea is the following. So we can construct the local model by use of this idea. And the local model looks as follows. So we take some local chart, which is inside the base manifold M0 with some coordinates xi, for instance. And this will be coordinates of degree 0. And in addition, let's take V, which is a Z star graded vector space. So this is the sum of all I from Z star. Just again, Z star is Z without 0. And here we only require that the dimension of Vi equals to less than infinity. So every Vi is finite dimensional. I think this is called probably, okay, we found a notation, we call this finite graded dimension. I mean, it's the graded dimension is the sequence of integers, the dimension of each Vi, and each of these integers is finite, right? So each Vi is finite. But if you take the sum of this, it can be infinite. So we do not require that all coordinates are concentrated only in finite number of degrees. Okay, now let's take V star, and V star is it's homomorphisms from V to underline from V to the ground field, let's say R, of course, in this case, such that V star I, so it will be Z-graded itself, and V star I is by definition the same as V minus I star. This is the requirement is justified by the idea that the contraction net between V star and V to R should be degree 0. So this bilinear map has to be of degree 0. Okay, and now just to construct the local model, we take what we expect, the symmetric algebra of V star with coefficients in smooth functions on U. This is our A, let's say AU. And now we construct A hat by use of the idea as above. So this is the projective limit of A divided by Fi of A for OI. So if you use the notation E equals to V cross U, right, over U. So if we construct a trivial vector bundle out of V, then we can write this as the completion of the symmetric of E star over C infinity U. And then we'll obtain, like this, we'll obtain local models, some Z-graded algebras over each coordinate chart if we have some cover, and then over overlap, we require that the change of coordinates or the gluing isomorphism has degree 0, and this only what we need. So now I probably do not have much time to explain this in details. Actually, I think the Sala paper, the second paper with Salnikov is a good exposition. It contains a little bit more than required, so we prove something for groupoids, which probably was not, which a little bit more general. It was an idea how to construct the idea which was not implemented in this paper, how to do everything in the singular case. But at least what I explain is explained in details. Now, whenever we use a ringed space, we can talk about isomorphisms. So we constructed a ringed space of Z-graded algebras. And the spectrum, the underlying geometrical object is called a Z-graded manifold. Okay, and then whenever we have such a construction, we can talk about isomorphisms using just our knowledge about ringed space. Nothing else is required. Also, there's some trick that actually one can show that what we construct like this will be immediately a sheaf. So there's sometimes some people talking about the great manifolds wonder whether we have sheaves. Everything here is fine because one can show that at each degree, if you look at the corresponding quotient A by Fi, A at each degree, it has finite rank. So there's absolutely no problem. We can construct a sheaf of Z-graded algebra, so a ringed space, and the underlying object is a Z-graded manifold. So whenever we construct this, we can talk about the category of Z-graded manifolds, isomorphisms of Z-graded manifolds, and ask a very natural question, which was solved by the end of 70s by Batchelor, and probably at the same time, well, so many people say that Gavetski did this the same at the same time. So, and it's called the Batchelor theorem. Which says, so the classical Batchelor theorem proven by Batchelor and Gavetski says that every smooth supermanifold is isomorphic as a supermanifold to a vector bundle over the usual manifold with shifted parity of the fibers. And here we have a similar situation, similar theorem, which is related to what I wrote before as an example. So for every Z-graded, or let's say Z-star graded, just using this, the idea that in degree 0, the coordinates are only smooth coordinates. So Z-star graded manifold is diffeomorphic to E over M0, where E is a Z-star graded vector bundle. So this is true in the smooth case. As I said, in the analytical case, like for supermanifolds, it can be wrong. So there are plenty of counterexamples when it's wrong. We listed a few of them in the paper. Then the first question, whether E is canonically constructed, right? So like you know that the Batchelor theorem not only says that every Z2 grade or supermanifold is diffeomorphic to a vector bundle over a manifold with a shifted file, but also say that this vector bundle is canonical, right? And here we have a very similar situation. And just to show this, I will come back again to yeah. Do I need what is better if I use a just okay, I will try to try. This one, right? Yeah. Okay.
You're erasing the board.
Until
So when you say the Z-star graded manifold, which I presume is not defined a priori using a vector bundle, like what exactly is that?
It's defined using the local model and gluing.
So the local model does need this vector bundle on over the charts.
Yes,
yeah.
It needs a vector bundle over a chart. Then we take the symmetric powers over 0 degree functions, smooth functions. Then we take the completion, and then we glue over double overlaps.
Okay.
Usual.
Okay, thanks.
I mean that I remember bachelor theory sometime for super manifold. Yeah, but now I forgot the thing that it's obvious that on super manifold or Z grade manifold is non-compact, right? Because it has a vector abundance.
There's nothing about compactness here.
So, it's obvious from definition. You can say, oh,
yeah, we'll see it. It's, I mean, the construction of the vector bundle will be obvious from the definition. Yes. Yes.
Such a 6-star vector bundle, we can keep degrading, right?
Yes.
We can declare whatever used to be. But if we construct a new manifold out of 6
okay, it will be diffeomorphic to it, right? In this great case. But if it takes such a vector bundle, you see that in addition, well, it's very important that in addition to Z gradient, it actually has 2 gradients. Let's call it positive and negative gradients, which count positive and negative degrees independently. Whenever we keep the structure of a vector bundle, these 2 gradients will be preserved. But in general, when we construct manifold, it will be mixed because only Z gradient is important. And actually, the idea which I explained before, right? So out of every Z graded, we can construct a Z cross Z graded. This is somehow we restore this situation, but we construct some other manifold with Z graded, and this will be actually this one. But let me explain now. Let me explain now a bit more. In a bit more regular way how to construct this E. And
N cross N, you mean, right? You mean N cross N, right? Not Z cross Z.
N cross N. But it's also Z cross Z. But what is important is N cross N. You're completely right, because this will be, yeah, you're right. Of course. It's more important, yes. Well, let's look, now suppose we have a Z-graded manifold or Z-star graded using these notations. So it's a Z-star graded manifold. For this manifold, it's a ring space over some even 0 degree smooth manifold. In general, a priori, it's not clear how this M0, if there are any map from M to M0 or the other way around. And we'll see, like in the super case, there is an embedding of M0 to M. Now, let's look at functions. So let's take functions. We'll use the notation O, OM, right? So there are functions on M. So this is a Z-graded algebra, the Z-graded supercommutative algebra. And it's obtained by gluing some completion of symmetric algebra over local charts, as I explained before. And now this algebra itself will be filtered, right? So O is the sum of OI for I from minus infinity to plus infinity. Let me remark one more time that O0 is not the same as functions on M0 because they are functions constructed from functions of degree, say, 5 and minus 5. We multiply, this will be still degree 0, but will be not a function over M0. So O0 is bigger than functions on M0. But this is a Z-graded algebra. And we can play the same game as before. So we can construct the filtration Fi of O. So this is everything. It's an ideal generated by the sum of OI for, sorry, OJ for J less or equal to minus I. So this algebra will be filtered again. And actually one can show that if you take the completion with respect to this filtration, we'll get again O of M. So it's because OM is already obtained as a completion. But what is more important here? Let's construct the following ideals. So I plus is everything generated by the sum of OJ for J greater than 0. It's an ideal. I minus is the same for negative degrees, or one can say that this is the same as F1 of O, or everything generated by negative degrees. These are two ideals. And now let's take I equals to the sum of two ideals, I plus and I minus. It's not a direct sum, just a sum. And now what is important, how now M0 can be embedded into the Z-graded manifold is the following. So okay, so first of all, let's take functions of O and divide by the ideal I plus. Okay, so this ideal is generated by all functions of positive degrees. When we take this quotient, it's a Z-graded ideal. This is the Z-graded ideal. So the quotient will be Z-graded algebra. The question for you: what will be the degrees of elements in this algebra? Non-negative. No, sorry. No, I plus is positive, not positive, right? So this will be it will be a Z-graded algebra. Actually, N-graded algebra. In non-positive positive degrees. And we can think of this as functions on some manifold. Let's call this M minus, which is now negatively not positively graded manifold. Now play the same game with I minus, right? And of course, I don't need to ask again. Of course, it will be functions on some non-negatively graded. Right, but what happens if you take O divided by I, which is the sum, not a direct sum, but the sum of I plus and I minus? If we get rid of all positive and negative coordinates, we'll get only coordinates of degree 0. So this will be functions on M0. So it means that we have the canonical embeddings of M plus minus inside M and M0 inside M. And this is actually well, and M0 into both M plus and M minus, but also inside M. And this is very similar to the usual Z2 graded case. That's like in supergeometry. Okay, now I guess I already spent quite a lot of time about the category of Z-graded manifolds, but it was a requirement I was requested to do this, right? Because probably not everyone knows perfectly how it works. And now let me come to the second part of this talk, to Q-manifolds, and I will sketch the results, some of the results written in the first reference in our joint paper with Camille and Vladimir. Okay, so suppose we have a Z-graded manifold. Then the functions on this manifold is a Z-graded supercommutative algebra. So it's a Z-graded supercommutative algebra. And now, as usual, like in the super case, we can look at derivations of fixed degree of this algebra and call this vector fields. And we say that it's a Q-manifold. The notation is coming from physics. In mathematics, sometimes people use the language, another language, GG manifold. If there exists a Q field, so it's a Q field. So it's a derivation. First of all, it should be a derivation of degree 1 of the algebra of functions. Second, we require that this is odd. And of course, if there's a Z2 gradient is coming from Z graded modular 2, this is a consequence of that. And then one more requirement is that this field is supercommutative. And means Q with Q, which is in this case 2 Q square equals to 0. Because the supercommutator should count that the vector field is odd. There are many examples of Q-manifolds which were known before the word Q came into this world. For instance, one of the best known examples, so it's example number 1, known from secondary school, right? So this is C shifted by 1 of usual manifold M0, right? If we take functions here, this will be differential forms on M0. And this one has a distinguished Q field, which is the Duran operator. Another example, number 2. Actually, all two examples I will give now are related to n-graded case. So suppose we have a Lie algebroid E over M0. So let's take at a Z-graded manifold E shifted by 1, which leaves over M0 again. So this again non-negatively graded Z-graded manifold. Then functions over M will be sections of lambda dot E star. And the Lie algebroid structure, so the Lie algebroid, the Lie bracket, actually it's in one-to-one correspondence with which is called Weintraub theorem from 97. Is in one-to-one correspondence with Q field, and the Q field is given by, there are many names for that. For instance, it's called, sometimes it's called Lichnerovich differential, but let's call this Lie algebroid differential, which is constructed the same way as the Duran operator by use of the same Cartan formula. But instead of the Lie bracket of vector fields, we take the Lie bracket in the Lie algebroid. Instead of the action of vector fields on functions, we take the action of sections of a Lie algebroid on functions by use of the anchor map. And example 3 is a Chevalier-Ehrenberg operator for a Lie algebra, or G Lie algebra, or in general super Lie algebra. Okay, so but there are also much more examples, and one of them we'll see one of them later. And now let's try to understand how a Q structure is compatible with Z-graded structure on a manifold. So on the on this board, I wrote that there are 3, or at least 2 canonical n-graded manifolds, non-negatively degree, with non-negative degree, non-positive degrees associated to a given Z-graded manifold. And now the question can be, well, one can say the geometrically m plus and minus are embedded in M. So the question is, the natural question is, if Q is tangent to any of them, to M plus and M minus. So the question, is it true that Q of plus minus, if you rephrase this algebraically, if Q applied to I plus minus belongs to I plus minus? So the question, it's a question, right? It's not a statement. The question for you, when it's true and when it's not. I plus is generated by everything of non-negative degrees. Oh, sorry, of positive degrees, strictly positive. I minus is generated by all functions of strictly negative degrees. So that's the product of all functions and functions of negative degrees, and here of positive degrees. And Q is a vector field. Well, it's not necessarily homological at the very beginning, but just a vector field of degree 1. right? The question, which of the statements is true, for plus or for minus? For plus, of course, right? So the statement for plus is true. The statement for minus may not be true, right? Sometimes it's true, for instance, if Q is 0, right? But sometimes not. We cannot guarantee this. It means that geometrically as a corollary, we have M minus another Q manifold. Q manifold, which is a submanifold, or Q submanifold inside MQ. And this manifold, this Q manifold is, as I said, is non-positively graded. Right? So it has functions of degrees 0, -1, -2, and so on to minus infinity. So you see, out of one Q manifold, we immediately construct another Q manifold, which is non-positively graded. And this gives plenty of examples, and one very important example. Yes? Mm-hmm.
Potential infinite dimensional, or you only consider finite dimensional? So as far as finite dimensional, once there is a formality theorem, and you can.
Which kind of dimension do you mean? If you look at the dimension of each degree, I always require that only finite number of coordinates in each degree. But of course, one can do something also in the infinite dimensional case. For instance, if you take two Z-graded manifolds and look at what is called homunderline, the space maps between them, it will be infinite dimensional. But in this case, what is important that the total dimension can be infinite, but the number of coordinates at each degree, the Z-graded dimension is always finite.
I see, but formality, for example, for your examples, it will work, right?
Yeah, it's not good.
I see. Okay.
For the formality, we need to. This works perfectly for. There's something can be constructed out of it. If you look at, for instance, AKZ model in topological field theory, which is somehow related to formality, of course. Then this formalism can be used to obtain for the space of functions on the space of maps, which will be infinite dimensional. But it's beyond the purposes of my talk, of course. So. So out of this, we construct an example of a Q manifold, which is just using any Q, Z-graded Q manifold, Z star. We construct a Q manifold, which is concentrated on non-negative degree, non-positive degrees. And inside this huge number of possible examples, there is one example. Let's call this example number 4, and it's concentrated in degrees less or equal to 0 degrees. And this is what is called Kashul-Tate resolution. And this will be the subject of the talk on 6th of March. The lecture will present a nice construction out of trees, binary trees, which is in forest, which is very, very nice. How to construct this using some linear data. And what does it mean that the Kashul-Tate manifold is given by the Kashul-Tate resolution? We require that the cohomology of all of this M minus are concentrated only in 0 degrees. So non-zero if I equals to 0 in general, and 0 if I is less than 0. What does it mean that we have that this is a resolution? Because you see that H0 will be some commutative algebra, which is not necessarily algebra function of smooth manifold. We'll see. I guess we'll have time to look at more details on that. And then the rest, the cohomology are 0. So it's really a resolution. There is a general algorithm how to construct Kashul-Tate. We have to find generators, CZGs, and then generators again. So finally, this procedure will converge, but it's a little bit non-constructive how to do this. So this always exists. I mean, at least in many good cases, like Noetherian case, and under some very moderate assumptions. And now let's look. Okay, so sorry, I forgot to give you the precise construction of a vector bundle in the Bachelor's theorem, right? So and then the construction of the vector bundle is the following. So let's take I, the ideal which I constructed before. So this is the sum of I plus and I minus, right? So everything which is the ideal which is generated of all functions of non-zero degree, right? And now, so this is the ideal of the embedding of M0 inside M. And let's take now the quotient I by I square. Right? So this quotient is related to conormal bundle. At least it's a Z-graded generalization of a conormal bundle of M0 inside M. Right? So if you want to construct algebraically a conormal bundle of some submanifold inside M, what should we take? The ideal of the submanifold and the quotient of this ideal by its square, right? If everything is smooth, this will be sections of the conormal bundle. And this is precisely sections of E star. So the E star is constructed simply as a conormal bundle of M0 inside M. So it's canonical. And one can show that the original manifold M is diffeomorphic to E over M0. And now let's do the following. So let's take a Q-manifold. And let's look at the map of F1 of O inside O0, right? Actually, here we should take everything in degree -1. And now let's take the quotient of O0 by the ideal I, right? So, and this is nothing but functions on M0, as we've seen before. If you look at this, the whole map, one can easily show that I square is in the kernel of this map. So actually, we produce a map from I to I square in degree -1 to functions on M0. So if you think a little bit, you easily see that this is true. And this is nothing but E1 star. And now it means that we immediately out of every Q field, we construct a section kappa in a canonical way, which belongs to gamma of E1. And this is what we call the curvature of Q. That's something which we don't see in the n-graded case, which appears in the z-graded case. And now the first theorem about z-graded Q-manifolds is the following. Well, as you see, this kappa is constructed canonically. It does not depend on the choice of coordinates, right? So let me give you some precise idea how it looks like. So suppose we have coordinates of different degrees. So our manifold, how the Q field will be looking like. So this will be some kappa I of x. So the sum d by d psi a -1, right? If you just decompose using arbitrary coordinates, and as before, the index means the degree of the coordinates. So these are all coordinates of degree -1, and that coefficient must be of degree 0. So these are functions of degree 0 plus the rest, which will be polynomial, which will have polynomial degree, at least polynomial degree greater or equal to 0 with respect to psi. And this one is precisely the kappa which we constructed in an invariant way. And the rest is polynomial. If you use coordinates, the rest will be polynomial with respect to non-zero degrees. And now the first theorem says the following. So let's construct U as the set of X in M0 U prime, you was already used, where kappa at this point X is not 0. So this is the set of points in M0 when the curvature is not vanishing. Then over U prime, we can find coordinates such that the rest will disappear, only this part will remain. So there exist coordinates. Such that only psi a x d by d psi a I remains. And it even does not depend on the coordinates. We can just kill the rep, which is polynomial. Here, just to do this, we use the structure of the algebra, the completion, and then we do this step by step by use of exponential of some vector fields. So that's pretty much technical, but it's also quite interesting. It shows that something non-trivial happens only over points where the curvature is vanishing. But the curvature is not vanishing, everything just a contraction with some section of something, nothing interesting. Now, what happens? Now we can say something about M minus. So we have seen that M minus itself is a Q manifold. Now, what can we do with M plus? As we have seen or mentioned before, Q of E plus is not necessarily inside E plus. But of course, it takes values here. It takes values in E plus. If you want to make it into a right statement, it takes values in E plus plus Q of E plus, right? Then it's, of course, it's tautologically obvious. And now, when this happens, we can generate an ideal by that and take the quotient of all functions by this ideal. So let's take the quotient of functions on M by the ideal I plus Q of I plus. Sorry, I minus. With a plus, it's true. I'm sorry. I minus. We want to get something non-negative. And now, what happens? So what we'll get will be, of course, non-negative because we kill all negative degrees, but we can kill also a little bit more because here it's a quotient by Q of I minus. And what do we get like this? So probably I do not have time to explain this in more details, but the idea that we'll obtain the zero locus of kappa, which is the set of X inside M, where kappa vanishes. So this is the zero locus of the curvature. It's not necessarily. In general, it's a singular manifold. It's not necessarily smooth, but it's somehow living in M. If the part M minus is of Koszul-Tate type, it's precisely the Koszul-Tate resolution of this singular set. And then what we get here, we obtain a singular, non-negatively graded Q structure over this Z of kappa. So instead of a smooth non-negatively graded Q manifold, we obtain a singular non-gradative Q manifold, which is living over the singular locus of kappa, of the curvature of a Q field. So in general, it looks like some Lie infinity, in particular, it's just Lie algebroids, but in general, Lie infinity algebroids living over singular graded singular manifolds, singular submanifolds of M0. And now the next theorem, it's not the last in the paper, but at least the last one I will tell about today is the following. Theorem. So suppose we have M. Suppose we have some delta Kashul-Tate resolution of some singular set Z inside M0. And the corresponding manifold we'll call M minus. And suppose we have a Q structure, non-negatively graded Q structure over Z, which is inside M0. Then there exists a Q structure on M, which is constructed out of M minus and this one, and non-negative, non-positive, oh sorry, non-negative, such that Q restricted to M minus gives the Kashul-Tate resolution. And moreover, any two extensions of this sort will be diffeomorphic. And here we should again use the structure of the algebra, the completion of this stuff. And actually, this sort of theorem, it's called, actually, it's an application of the homological perturbation theory, which is known in mathematical physics, just done in some regular way. Well, here it's because I'm already out of time, so let me finish with theorems, and let me tell you that in the first paper, normal forms of Z-graded manifolds, there is also computations for cohomology of vector fields on Z-graded manifolds. One can show that they are concentrated if the negative part of a Q-manifold has a Kashul-Tate type, then the cohomology of vector fields is concentrated in either in positive degrees, or in also a little bit in negative. So then this is probably related to what is called the tension complex, but I'm not completely sure. I think it's at least we did not figure out the right literature for that. And then there are also many examples. Many of them are related to just the cohomology of vector fields. So what happens in the Kashul-Tate, what happens in the Kashul case, even in the Kashul case, even the case of complete intersection, the cohomology of vector fields is not very trivial, and so on, so on. So that's for that I refer to the paper number 1. Okay, thank you.
I have a question. So you just mentioned about the homological perturbation theory. So it's related to homological algebra and kind of higher structure or something related to.
Everything is related to higher structure because everything is related here to L-infinity algebras, for instance. Yeah. But when I said about the homological perturbation, I meant precisely this algorithm, how to extend non-negatively graded Q field over a singular set to a big Q field over the bigger set, such that the negative part gives the Kashul-Tate resolution. This is precisely the homological perturbation theorem. That's an application of it. Just the technique which is used to do it, right? But as I said, of course, well, many of these things were just invented or used by Kontsevich to prove, for instance, to prove formality, and then many other people.
Yes, that is a
Q-manifolds, L-infinity, but for him it was probably just a part of technique to just use to prove formality, right? So, but everything is, of course, everything is related to high structures.
Yeah.
So that's compared to Kontsevich formality, this of course is just a cleanup, right? Because it was a revolutionary idea for him.
Yeah. So that's also the thing related to some physics problem.
Yeah, of course it's related to physical problem because I did not mention, of course it's related, for instance, to BV formalism because it's related to non-Lagrangian BV theory. If you include also Poisson brackets, it will be Lagrangian because this type of Q field such that the non-positive part is Kashul-Tate resolution and negative part is is something which is living on a singular case. Of course, it's related to physics. It's just BRST. Also, yeah. This.
I have a religion about this.
Oh,
So
go ahead, Vladimir.
since the result you are presenting is also constructive, right? I give you a Q structure and you massage it into the canonical form, and we know that in physics some gauge transformations are related to Q homotopies. So maybe it is some kind of, it is maybe related, that's why I'm saying religion, to some smart way of gauge fixing.
Yeah, sure. Yeah, I think it's a subject not for one lecture, but for the whole.
Yeah, no, sure. I mean, it's totally
right.
understood.
Of course, we are on the same page, right?
Yeah.
Yeah, of course. Yeah, but what physicists also like when this is infinite dimensional, but infinite dimensional some controlled sense. For instance, we can use this in jet spaces, and then it becomes more interesting. But also many things will survive. Because jet spaces is a nice way how to work using some finite dimensional technique with infinite dimensional spaces, right? So also, yeah.
Just wanted to make sure I understand. When you're talking about this possibly singular Q structures, you just mean like a ring space with a graded ring and
here, even simpler. So you can look at some singular submanifold, which is given by some ideal, finitely generated ideal functions on M, right? So you take some vector bundle which is living over M0, some positively graded vector bundle over M0, restricted here, construct n-graded, whatever it means, singular space, which will be singular only with respect to 0 degrees, but regular with respect to higher degrees, and take the homological derivation of degree 1. This is what I mean, right? So whenever we have that, and whenever we, in addition, have a Kashut-Tate resolution of this space itself, we can construct a Q field over a bigger space, which is a combination of this positive part and the Kashut-Tate resolution, such that the negative part of this Q field will be precisely the Kashut-Tate resolution.
Be specific, so to understand one half of this, implication. So when you say Q structure over Z, what does that mean?
Q structure over Z, Q structure on a Z graded manifold. It's not over Z.
But Z is not a manifold. That's the point.
No, sorry.
Again,
I should name a different name. It's not integers, right? So it's not a manifold, right? But I mean, by this I mean just algebraically. We have an ideal of that, right? So we have functions of degree 0 over M0. We have an ideal here. We require that this ideal is finitely generated to have a good Kashut-Tate resolution. Okay, and then it's we have an algebra of functions on Z, which is simply the quotient of functions here by the ideal. We add some degrees, some positive degrees by use of a vector bundle here over M0. We take a derivation which is of degree 1 of this bigger algebra, which is homological.
Okay,
and this is a singular, non-negatively graded Q manifold.
Okay.
So just in a purely algebraic case, right? Because we
without requiring local regular charts.
They cannot be regular with respect to Z inside M0 because it's irregular, right? Yeah. But they are regular with respect to positive degree coordinates.
Okay, I understand. But with respect to the singular base,
singular,
then it's just a ring space.
Singular, yes.
It's a ring space. Okay.
Exactly. For that, if it's smooth, then everything fine. It's just n-graded manifold. We do not need to extend it somewhere. But if it's non-smooth, then we take the Kashut-Tate resolution and extend. Then it's Then the whole extension, to be totally honest, the whole extension such that the non-positive part gives the Kashut-Tate resolution is the generalization of a non-negatively graded Q manifold, or Lie algebroid over singular space, or Lie infinity algebroid over singular space. Because, we make something into smooth, which was not smooth before.
So, if there are no more questions, let us thank speaker again.
Thank you.